Okay, so right now we're looking at the graph of 1 over r as a function from the two-dimensional Euclidean space R2 from the plane into the real numbers. And the graph of the function 1 over r is shown in light blue here. And I've drawn a cylinder centered at r equals 0 in the xy plane to emphasize an important aspect of this graph. Okay, so first of all, let's note that if we take the volume under this surface and we look at the volume that's cut out by a cylinder of arbitrary radius, so let's say I just change this cylinder to have a radius of 2, let's say. The cylinder can have any radius, then the volume of this surface underneath the circle cut out by the cylinder is precisely the area of that circle. Okay, so if I integrate this function 1 over r over a disk centered at the origin, the resulting volume will equal the area of the disk. Okay? Now, furthermore, if I fix an angle, so let's go ahead and fix an angle here. Let's say x equals 2y. So that fixes my angle to be arctangent of 1/2. Okay? So then what I can do is look at the cross section of this surface along this plane of fixed angle and integrate the cross section of this surface from 1. Let's fix this cylinder back to 1. So I can integrate this I can integrate this surface, the cross section of the surface, from 1 to some outer radius r, and the result will be the natural logarithm of r. Okay, so if I take the cumulative area underneath the cross section of this surface from the value 1 out until a fixed radius r, or inward, then the area, the signed area underneath that, is going to be the natural log of r. And that's the height of this surface in dark red that I've just plotted. Okay, so that's where the height of this surface comes from. Now this surface is very important. This is the surface natural logarithm of r. This turns out to be the fundamental solution to the Laplace equation in 2 dimensions. Okay, so the Laplacian of this function is equal to 0 everywhere except for the origin. At the origin, the Laplacian is a delta mass. Okay, so what that means is that if I fix a point that's not on the origin and I zoom in to this surface at some fixed point, let's say, then what I should have is that this point should look like the average of the points nearby it. Okay, so if we discretize the Laplacian with respect to the Euclidean coordinates, then the best approximation up to order of like the square of the grid spacing is going to be the value of the function at the center point of some grid is equal to the average over the 4 neighboring points. The value of the function of the 4 neighboring points. Okay, so somehow this function locally or even non-locally, globally, it looks like every point, if you take a circle in the xy plane centered at that point, and you average the function's values over that circle, you're going to end up with the value of the function at the center point. Okay, and that circle doesn't actually have to be small. It can be as large of a circle as you want, so long as it doesn't pass through the origin. Okay, but we're going to focus in on kind of the local averaging nature and try to understand why this particular graph satisfies this nice local averaging property that is the result of the fact that it solves the Laplace equation. Okay, so why is this the case? Well, let's go ahead and put Cartesian coordinates on the xy plane underneath this surface. Okay, so I'm going to now focus in on the domain, and you can picture the surface as kind of being viewed as as graphed on top of this domain. Okay, so this is the xy plane above which the surface is graphed. And I'm going to go ahead and put Cartesian coordinates on the xy plane. Okay. Now, what I want is a solution that is radially symmetric. Okay, and that's because we're solving the Laplace equation essentially in all of R2 set minus the origin. Okay, and so the Laplace equation is rotationally symmetric, which means that I want to look for a solution that satisfies radial symmetry. So that means that if I pass now to polar coordinates, so r theta coordinates here, and I went ahead and plotted r theta coordinates, the x-axis shown here is actually the theta. Okay, so the horizontal axis is now theta, and the origin gets blown up to a line. So the origin of the plane gets blown up to a line at the base here. And then these dotted lines in purple are spaced out by a factor of pi over 2. And so those dotted lines in purple are the x and the y axes. Okay, and the x and the y axes get spaced apart, uniform spacing. And then we have this this cylinder, essentially, the cylinder, which is periodic at the boundary. And then the y-coordinate, the vertical coordinate, is the radius. Okay? And so these are polar coordinates. And I went ahead and showed the image of this Cartesian lattice here. So I took a Cartesian lattice, and then I did the polar coordinates transformation and brought that Cartesian lattice into its image in the polar coordinate system. Okay? And so you can see that we know that the Jacobian of the transformation from the r theta plane into the xy plane. So if I went ahead and did the inverse transformation, which is how we normally think about polar coordinates, where I map the r theta plane into the xy plane, that transformation is going to be given by x equals r cosine theta and y equals r sine theta. The Jacobian of that transformation has determinant equal to r. Okay. And so then if I apply the inverse function theorem and look at the inverse mapping from Cartesian coordinates into polar coordinates, then the Jacobian there will have determinant 1 over r. Okay, and it's actually going to look like a rotation by an angle theta, and then a scaling, a horizontal scaling by a factor of 1 over r. Okay. So as r increases here in the r theta plane, the xy grid essentially gets rotated by an angle of theta locally. Okay, so it gets rotated by an angle of theta, and then it gets stretched. Its volume gets stretched by a factor of 1 over r. But in fact, we can say more. Okay, we actually observe that the vertical spacing of the grid points here, the grid lines, the vertical spacing is actually constant. Okay, it's going to depend on the angle theta, but it is constant. But the horizontal spacing is getting compressed as r increases. So the horizontal spacing is getting compressed by a factor of 1 over r. Okay, and the reason for this is that essentially we're taking circles. We're essentially looking at circles in the xy plane, and then we're kind of slicing them and folding them to be flat lines. And so for larger circles, right, a larger circle is just going to get mapped to a horizontal line that's higher up on this r theta plane. And so it's going to get compressed more, right? The horizontal lines are getting compressed because there's circles. The perimeter of a circle is scaling by a factor of r as you increase the size of the circle. And so that length is getting compressed to a fixed length of 2 pi here, which means that it's getting scaled by a factor of 1 over r. So we have this horizontal compression in the r coordinate by a factor of 1 over r. Now, if I plot and then the horizontal compression is by a factor of 1 over r. There's no vertical compression, however. Okay, there's 0 vertical compression. So now I know that the natural logarithm of r actually, how does it distort mass? Well, the natural logarithm of r it's going to stretch um, the real line by a factor of 1 over r, right? Just by, again, the fact that the derivative of the natural logarithm is 1 over r. That represents the local volume distortion, the local length distortion of the natural logarithm. So if I go ahead and distort the vertical axis now and plot the vertical axis logarithmically, then what we're going to see is that the vertical spacing will scale like 1 over r, just like the horizontal spacing in this diagram. So let's go ahead and do that. We're going to go ahead and put the y-axis into a logarithmic scale, okay? And now we get this beautiful diagram here. And let's zoom in slightly. So this would be to a single, we're going to zoom into a single quadrant of the xy plane, okay? So going back over here, kind of just zooming into, let's just say, one of the quadrants. Let's just say it's the positive quadrant that I care about. If I zoom into the positive quadrant, then that would be, yeah, that would be this exact thing that I'm trying to zoom in on here. Okay, so we've zoomed into the positive coordinate now. And let's actually just isolate this. So let's set the x-axis to go from 0, x-axis is theta, remember, 0 to pi over 2. So this is exactly the first quadrant. And then I'll set this to be plotting it logarithmically. So let's just do it like so. Or maybe I'll just go to 10 and then 0.1. Let's say. Okay, so this is the first quadrant, and now we observe that that the vertical length is being distorted by a factor 1 over r, and the horizontal lengths are also being compressed by a factor 1 over r as I increase in the r direction. Okay, so now if I go ahead and plot, let's go ahead and plot some specific grid lines here, just so we can get kind of a visual sense of perspective, a sense of perspective on how this is working here. So I went ahead and plotted the same exact box, okay, in both the Cartesian and the polar coordinates. Now, if I move this box around in the Cartesian coordinates, I can see that I'm just looking at kind of a square, four adjacent squares in my grid, and I'm kind of moving them along the line x equals y at a uniform speed. Okay? So now let's go ahead and do the same thing. Now let's just take these lines in yellow and map them onto the logarithmically radial scaled polar coordinate system. And we get something that looks like this, okay? So now I can see exactly the way that, that this grid is scaling in my polar coordinates, but the radial coordinate is plotted logarithmically. I can see that the aspect ratio is preserved, okay, of this grid, which means that the ratio of the vertical to the horizontal distances is the same, okay? So if I want a radially symmetric solution to the Laplace equation, then I need it to locally be the average, its value at the center of this grid near here needs to be the average of its values on the outside of the grid. And if I want the solution to be radially symmetric, that's equivalent to requiring that it's constant with respect to theta, okay? So if I require that, the function is constant along horizontal lines in this diagram, in this r theta diagram, and I understand that, well, my grid spacing, my aspect ratio is constant, is fixed, okay, then the solution to the Laplace equation with respect to these coordinates is just going to be a plane, and it's going to be a plane that goes through the theta axis, okay? So that's precisely what I've graphed here. Okay, so if we graph just a plane where now this y coordinate is r and the x coordinate is theta, okay? And I graph this plane, then, then this plane is certainly going to behave like, if I pause this animation here, if I pause this animation at any fixed time, then I have a grid with constant. Let me pause it at a better time. Sorry. So I have a grid with constant aspect ratio, and so the plane, if I look at these 4 points on the grid here, if I can get this thing to work. Sorry, y'all. Okay, it's not being nice. There we go. Okay, so if I look at these 4 points, then a plane is going to satisfy that these 4 points, the average, as long as I make this grid fine enough, right, so that it's truly, we're truly getting some parallelepipeds here, then the average of the plane around these 4 points is going to equal the value of the plane at the center, and that's just due to the fact that the plane is linear in the vertical coordinate. The vertical coordinate is the natural log of r. Okay, so yeah, I plot a plane in this coordinate system, and I observe that due to the fact the aspect ratio of this grid, this mesh size, is fixed, then if I take a fine enough grid, that plane will look like everywhere it will look like constant in the theta direction, and also in the radial direction it'll be equal to the average of the surrounding points. Okay, that's a solution to the Laplace equation. Now if I go ahead and convert my coordinates back to Euclidean coordinates, well, the first step is just converting this diagram back to just ordinary polar coordinates. So that means we're going to put the y-axis back to linear. Okay, and now we get something like this, and the graph of our plane becomes the graph of the natural log of r in the r theta coordinates. So now our plane gets transformed to this surface in the r theta coordinates. Okay, and then we just transform all the way back to Cartesian from the r theta coordinates. We transform back to Cartesian. We get our Cartesian coordinate system, our friendly, beloved Cartesian coordinate system, and the graph of the resulting surface is precisely here, the fundamental solution. Okay. Another way you can think about this is that if you partition the z-axis here in this graph, in the Euclidean graph, okay, into intervals of fixed width, then you look at the preimage of those intervals under the map, which is the fundamental solution. The preimage of these intervals on the z-axis of fixed width is going to be a family of concentric circles, and those concentric circles will have radii, which are decreasing and stretching at a factor 1 over r. But the area of those concentric circles will be constant. Okay. So we can think about essentially taking this surface and then inserting a branch cut somewhere. So maybe our branch cut is on the, we're going to take maybe 2 branch cuts, one along the line theta equals 0 and one along the line theta equals pi halves. And then we're basically going to take this surface and fold it, kind of compress it inwards along this polar coordinate transformation to get here, okay? And then our grid is no longer of a uniform aspect ratio, but if we plot the grid logarithmically, if we plot the radius logarithmically, then all of a sudden our grid is of a uniform aspect ratio. And then we can just determine the solution of the Laplace equation with respect to this mesh. With respect to this mesh, the solution of the Laplace equation is just a plane, which is constant, horizontally constant with respect to the theta coordinate. That is telling us that essentially the average of this function along the Cartesian coordinates, along this Cartesian mesh grid, the function is locally the average of the neighboring surrounding points. So yeah, this is something very beautiful. Something that I need to think about even more. But turns out that for any solution, so this is a graph which minimizes surface area locally, and any solution of the Laplace equation, in fact, you can write it as the convolution of this fundamental solution with your source term. Okay, and so this fundamental solution is very fundamental in many ways. There's a lot of depth to this, and I really think you all should go check this out on your own and plot this out on your own. I'll show you how I plotted it. I mean, I just plotted. I fixed x and y to be increasing in increments of 0.25, and then the image in the r theta plane is just, you know, r is equal to, let's say in this case, x over cosine theta, and so then you just plot r is equal to the x value, in this case 0.25, let's say, over cosine theta. And that's the image of the grid in the r theta plane. And then you can plot the y-axis logarithmically, and just see the beautiful scaling invariance that occurs, and that this aspect ratio is fixed. I just think it's really beautiful visualization, because it kind of puts into perspective geometrically what these polar coordinates are doing. And in fact, maybe thinking about polar coordinates with a logarithmic radial scaling is better in some instances, in some cases, just because when you look at the image of the Cartesian grid, the aspect ratio is preserved.